Hello, this is my Lab 3 Black Hole and Orbit. Introduction. This lab has two parts. Part 1 is to quantify the mass of the black hole. As a result, the mass of the black hole is 1.405 times 10 to 34 kilogram. Part 2 is to computationally create a figure 8 orbit for the spaceship to go around a planet and its moon. As a result, I haven't achieved a figure 8 orbit yet, but at least the spaceship doesn't crash into the moon or the planet by the max time. Next, fundamental principle. The first important equation that I use in this lab is position update formula from the average velocity, and next is the velocity update formula from the Newton's second law, F net equal dp over dt, also known as the momentum principle, and F net can also be found with F parallel plus F perpendicular. And the last important equation is Newton's law of universal gravitation, because in this lab we assume that there is only gravitational force exerted on the system, so F net will be equal to F graph, and this is the equation for f graph, and set the f net equal to f graph, and using algebra we can isolate the m2, which is the mass for the black hole in this case, and I will use this equation in close grip later on. The first part of this lab is to find the mass for the black hole, so the system will be the black hole, and the surrounding will be the star. And here's the initial condition that I was given, and in the calculation loop I will find the f net as the star moves around the system, and plug that into the equation to find the mass for the black hole. Then I'll use another for loop to find the total of the mass for the black hole from many different results from the while loop above. Then finally divide that by how many times it counts and print out the average of the mass for the black hole. And here's the result that I got as a code run. And here the Fnet parallel, Fnet perpendicular, and most importantly is the mass for the black hole is 1.40501 times 10 to the 34th kilogram. The second part of this lab is to find the orbit for a spaceship to go around a planet and its moon in a figure 8 shape by testing different initial velocities. Therefore, the system it will be the spaceship, and the surrounding will be the planet and its moon. And here are some conditions initially and constant. Then I set the speed of the ship according to the speed of the moon. For the x component, I multiply by 0.75, and for the y component, I multiply by 1.5. In this calculation loop, I find the net force on the moon and net force on the spaceship. Then I update the moon velocity and position as well as the ship velocity and position to keep things moving. And here's the result of my code. Even though the orbit of the spaceship is not in the figure 8 shape, it never crashes into the moon or the planet by the end of the time max, which is the 700 hour by default. Some sources of error in this lab include rounding error. In part 1, as the tiny numerical error can accumulate over time, as a result, the mass of the black hole can be slightly different from accuracy. Secondly, the method of trial and error used to find the initial velocity may not be optimal because it's only involved guessing, so I might not get the best answer yet. And lastly, it's because this lab is only created computationally, so there's a lot of assumptions and therefore is far from the same in reality. Additional questions. How are the net force and its parallel and perpendicular components different from the rate of change of momentum in its parallel and perpendicular component? So by the definition, the net force is the cos, meaning it's the vector sum of all forces, and the rate of change of momentum is the effect, meaning it relates to the object's velocity over time. Despite that, the parallel component of the net force represents the change in speed. Meanwhile, the parallel component of the changing momentum represents how fast the speed is changing over time. In the same way, the perpendicular component is the net force, explain the change in the direction, while the changing momentum means how quickly the object is turning over time. What if a system has all of the following: a black hole, a star, a planet, and a moon? What do I have to include in my computational model? I will have to include the net force, the net gravitational force for each of the object that due to every other object in the system. For example, the force on the star is due to the black hole, the planet, and the moon, and so on. I also have to account for the Newton's third law. The law states that each action has an equal and opposite reaction. For example, if the moon pulls on the planet will pull back on the moon with equal force. And so, would there be any dominant interactions, or would they all contribute more or less equally? And the answer is yes. The dominant interactions are the black hole on the star on the planet, and the planet on the moon. The rest are smaller but still matter in the long-term accuracy, especially in a chaotic system like this. And that is my presentation. Thank you for listening.